start in a minute. So I just want to say what a pleasure it is to have everybody here. Have some potential ones.
Okay, first I'd like to thank the organizers for inviting me to give a talk about what we have done over the few years. Today I'm going to talk about emergence of room temperature ferroelectricity at reduced dimension, and this work is supported by NSF DMRE program. So this work has been done in collaboration with a very talented group of people, and then including my group, and then theory groups, and Nebraska, and then Temple University, Shifanu. And then we have microscopy, and Raman, and then some other measurement done is the PFM measurement, Alex Grubman's group. So these are two aspects of the dimensionality of the ferroelectricity. And first of all, when you use this very reduced dimension, there's a potentially you can use ferroelectric tunnel junctions. For example, here, when you have a very thin films of ferroelectric, and you can write the domain, but at the same time, you can have a very different tunneling resistance as a function of Fourier direction. So that's a very important physical phenomena and applications in reduced dimension. And then fundamental point of view, I think these well-known papers of the size effect of the barium titanate as a function of thickness, and when you go reduced dimension and then disappearance of the ferroelectricity. And then, but we are trying to understand a new mechanism to overcome this size effect, and then in the ferroelectric systems. So one system we have looked at is non-ferroelectric material, and then trying to study this emergence of the new phenomena. So most of the perovskite oxide, ferroelectric material or dielectric materials, and always we have like a small amount of the defects, especially point defects exist. But we have very little know about and little control about this point defect, especially this very complex material system, and create a lot of vacancies and then anti-site disorders. Also, this local inhomogeneity, there's a hypothesis and create, they call polar nanoregions in dielectrics, and then they're creating this kind of disconnected polar nanoregions, and then macroscopically it does not show any ferroelectricity at all. And then, but we are interested in utilizing this naturally existing PNR in dielectrics. So we have, many years ago, we have been working on this strain-free, the dielectric thin film strontium titanate. At the time, we have compared this strained strontium titanate or neodymium gallate, and it has a very strong ferroelectric behavior. And then, however, still we see that some kind of ferroelectric behavior, very, very short period of time, and then strontium titanate, there's no strain involved. And however, this system is relaxed so quickly when you write this one by PFM, and strain-free one, it relaxes so quickly, and then that's why it's almost impossible to measure this macroscopic electrical measurement. In contrast, the strain one and lasts much longer than strain film one. And the relaxation here is, we can see that bismuth ferrite doesn't relax at all with the long period of time, and strain-free relaxes much faster than strain film. So we look at this one by Raman, and then we have an indication of Raman, and this strain-free strontium titanate, this is grown by single crystal strontium titanate single crystal target, which does not have clear the indication of the ferroelectricity of PNR. And however, you see that clear indication of the polar nanoregions in the system. When you increase the temperature, and then from 10 Kelvin, and then still see that there's some signal up to the room temperature, and then this is some kind of indirect evidence of the nanopolar regions. But how we can understand this nature of the nanopolar regions? And then this nanopolar region, this paper is formation energy of defect energy of different type defects in the strontium titanate in dielectric material. As you can see that most stable defects in this system is anti-site titanium, and then creating strontium vacancy site occupy the titanium ions, and that creating lowest energy and the most stable configuration. And then compared to just the vacancies, so this is more stable. And then another theory paper is previously, this titanium ions occupy this strontium vacancy site, and that's because large volume inside here, and then has creating very large displacement, like a 0.8 angstrom of the displacement, which is much bigger than most of displacement in titanium ions in barium titanate, lead titanate. And then, so we performed this kind of the DFT calculation in collaboration with Shifan Wu and Temple University. And then his calculation is very similar, like a 0.8 angstrom of the displacement. But very interesting part here is this 3x3x3 supercell calculation shows in center part a very large polarization around the 40-55 microcoulomb per square centimeter, and average about 3x3, like about 25 microcoulomb per square centimeter, which is substantial in size of the polarization and creating by this small one anti-site titanium and strontium site. And then this also, there's some barrier between this configuration of 01 and 001. And then you have some kind of barrier. The most stable direction of polarization is 100 direction on cubic perovskite structure. So this is interesting. Natural formation of PNR is strontium titanate, and this intrinsic point defect is naturally exist in most of the thin films, even though we grow this material very, very clean and the stoichiometric, very close to stoichiometry, it always does exist. However, we do not see this ferroelectric behavior because these nanopolar regions completely disconnected and does not actually couple each other. So how do you make this one and couple each other and then make a ferroelectricity, emergence of ferroelectricity? So just creating this one very reduced dimension comparable with the size of nanopolar regions, and then screened by the bottom electrode and surface charge, and then possibly you can stabilize this polarization in the nanopolar regions. So the dimension control is a key. At the same time, you want to grow these materials at very, very uniform thickness and high quality, and that's one of the requirements of this. And then we also collaborate with Longking Chen at Penn State. He performed the DFT, the phase field simulations, and they're reducing the dimension from large size of the film thickness to reduced dimension. And he clearly see that the relaxation of the polarization, and you can see that the thicker film relaxes much faster than these kind of thin films. For example, 12 in your cell and never relax. And then so you can see that how much of the polarization maintained when you decrease the thickness of the thin films. So he did that, this polarization versus thickness, and based on this his phase field simulation, and then appearance of the large polarization around the 15 units, 24 unit cell, this crossover, and you get you can have a large polarization only thin regions of the films. So how do you make this test experimentally validate and this kind of experiment, this kind of system? So we have the system to grow atomically controlled growth of strontium titanate heterostructures with the bottom electrode, the strontium luthenate. And we use a single crystal strontium titanate, the bottom the substrate, in order to make a strain-free. It's an intrinsic, just the nanopolar regions of study. And then we have single surface termination of the titanium terminated surface. And then we grow this the strontium luthenate using this read control, this one controlled. And then each layer oscillation corresponds to one unit cell of the thickness. So we have a very tight control of the film thickness. At the same time, we can measure this the structural information by electron diffraction pattern. So we integrate this read into our the pulsar laser deposition system, and then you clearly show that you can see that the read pattern is maintained, and then during the growth, and you can have very nice oscillation of growth of strontium titanate in the system. And in order to do this test of this bottom electrode, and then we need a single crystal and the metallic oxide electrode, which has the same crystal structure and almost the lattice parameter, same lattice parameter, coherent growth. And they use strontium luthenate, which is a very good metallic oxide, screening perfectly well. And then you grow this material, for example, strontium luthenate, strontium titanate, and heterostructures. You can see that beautiful step structures, and then you can count and then number of unit cells. This, for example, 6 unit cell barriers, and then top and bottom electrode can be maintained. And for example, structure after grow, these heterostructures, you can see that surface almost like same as the single crystal substrate, and then the interface is atomically sharp, and you can actually count number of the barium titanate layers. This is one example. I'm showing the different material, barium titanate, but this whole material is a stack and without any creation of the other dislocation or defects. But still, we have some kind of point defect which cannot be observed here because of that. It's very challenging. Is observing this the detection of this point defect in microscopy and other techniques. And then so we grow the strontium luthenate bottom electrode and strontium titanate, change the thickness of the strontium titanate, and then 12 unit cell to 120 unit cell. And you can see that number of oscillation is clearly observed, and then read pattern is very clean. And you can see that there's no difference between the strontium titanate single crystal substrate and then strontium titanate film on top of the bottom electrode, and you maintain almost perfect structures. And then one interesting part here is when you grow this material, we use a strontium titanate single crystal target, which is same substrate material as a single crystal substrate. And then so stoichiometry is in terms of measure this stoichiometry by RDS and then WDS. And then the composition stoichiometry almost close to 1-to-1 within the experimental error. So that's less than 1% of the small strontium vacancies. And then that creates enough nanopolar regions and creating emergence of ferroelectricity. And then you see that this is strontium luthenate and this thickness oscillation. This is actually the experimental data and the fit of the strontium titanate. And you don't see that the separation of the strontium titanate single crystal substrate and thin films, and that's on top of each other. So that means your material we grow is very close to the single crystal, but still we have some point defects in it. So we look at this one is strontium titanate PLD grown one, and you clearly see that the Raman shows a nanopolar regions, polar nature up to about 400 Kelvin. And then we also look at this normalized intensity. It drops around the 400 Kelvin, disappears. And then in order to test this nanopolar regions, existence and PLD, grown thin films, and we asked these films from Susan Stammer's group at the UC Santa Barbara, and they developed like they call hybrid MBE. It's they use the chemical source of the titanium TTIP source, and then control the much closer stoichiometry, and then which is very similar to growth process or gallium arsenide. And this is the absorption process. So whenever you have titanium, it only sticks when you have a strontium atom is attached. So it's a kind of plateau around a certain temperature region. You can have a very tight control of the stoichiometry of strontium to titanium ratio. And then when you do that, and when you look at those same films are much weaker, and then there's no existence of those the Raman peaks, and that means there's no nanopolar regions is at room temperature around, but still room temperature very, very tiny ones. So you can see that much stronger nanopolar regions due to this strontium titanium anti-site the ions, and then creating nanopolar regions. So we look at this one by microscopy STEM work. And STEM is very challenging because the displacement measurement is very difficult. It's a very small amount of displacement. And then what we did here is you can see that there's certain regions here, and this oxygen and this oxygen with respect to the titanium. And then you can see that this displacement is much, in this case, you can see the displacement with respect to this ion, and then this region, there's no displacement. So titanium ions, you can see that titanium here, and then oxygen, you see the oxygen displacement, and map it out, these regions, and you see that certain regions, these red regions, shows pointing down polarization, and then shows some existence of nanopolar regions, not all connected, but you see that these features. So how can you test this when you reduce the dimension is emergence of ferroelectricity? So what we did first is use this PFM measurement, is 120 unit cell thick, very thick films, so strontium titanate, and you write the domain is plus and minus domain, and then you don't see any contrast at all, which means you cannot write the ferroelectric domain. It just disappears quickly. However, when you decrease the thickness, like 120 to 60 unit cell, you see certain regions, but not very stable, and then it disappears gradually. But when you have a 12 unit cell, it's very stable. It never disappears with a long period of time. And then, so this is very first test of, okay, this reduced dimension, and then is emergence of ferroelectricity. It's all measurement room temperature done. Only happens and then reduced in dimension. So this is very different from these other types of ferroelectricity. And then when you reduce dimension, and then ferroelectricity is suppressed. But here, non-ferroelectric material, and then is ferroelectricity actually emerged and enhanced at the reduced dimension. So in order to test this one, and then we have a switchability, and then we do a switching, and then not only, and then the right domain, we can switch the domain up and down. And you can see the stability of the ferroelectric domains we wrote here, and very comparable with the barium titanate with the same thickness of barium titanate. And then when you have a thicker film, for example, 102 unit cell, unstrained one, is relaxed so quickly, so that's why we didn't see any contrast in the domain structures. But when you have this one, is a thinner one, is a 12 unit cell one, is very similar to barium titanate. So you also rule out any possibility of the surface charging effect or any like injection of charge. So we did this measurement using mechanical switching. It's avoid any the ion motions or anything. So what happened is when you press the surface of the strontium titanium by AFM tip, and then you can create the flexoelectric effect and then make this kind of symmetric weld. And then can you write the domains? So you have like a 12 unit cell one. When you increase the force, 12 to 100 nanometers, and you can see that is change of the writing domains. So we can see that the features here, excluding extrinsic effect and the surface charging and electromigration oxygen vacancies. Okay. And also, we want to test this one. One important test is ferroelectricity disappears when you increase temperature, because we know that Raman data shows around the 400 Kelvin, it disappears, this Raman peak. So we can see it's increasing temperature, 300 degrees to 400, and then this one gradually disappears. So only see the 300 room temperature, but high temperature, we do not see it, is consistent with the intensity of the Raman intensity of this peak. And then finally, we want to test this one to electrical measurement. It's very challenging because thickness is only 12 to 24 unit cell, extremely thin. So leakage is very big. And then that's why the atomic layer controlled growth without any pinholes is very important. So we made this about a 5 micron diameter device, which is a very, very small one. And we patterned this device with ion milling. And then you can see that 120 unit cell thickness one is no remnant polarization at all, measured by normal polarization P roof or pond measurement. There's nothing here. But when you go 24 unit cell thinner one, you can clearly see that it's a remnant polarization, and then we can switch this one up and down. So this is one of the important tests, including PFM and the Raman measurement, and then mechanical switching. But this is another evidence of we have room temperature ferroelectricity. So what is the implication of this one? And then, so this is the work done with several groups. But this is Alexei Grumman's and then the work in Nano Letter paper, which shows when you have this ferroelectric layer, and then when you switch this one, you change the barrier height, barrier shape, and then you can have a different IV curve, which means depending on the switching polarization up and down state, you can have a dramatic difference of the tunneling resistance. That is one of the important way to make a device, a logic device. And then also, we look at these regions, polarization, up and down regions, nanopolar regions. Whether a down polar region, you should have a large conductance of the tunneling conductance. And then these regions is not going to have this large polarization conductance. So we look at map out this, you see clearly that regions of high conductance, and that is indication of nanopolar regions. And you switch up everything, you do not see anything here. So that is another is interesting observation. PNR as original ferroelectricity, TR, tunneling electrical resistance in ultra-thin strontium titanate. And then also we increase the force, and then increase the force, higher loading force, and increase the area of the down polarization region. You can see that conducting region spread bigger and bigger, and which is not homogeneously, but you can see that the switching of the large area nanopolar regions by mechanical writing. So what is the actual implication of this ferroelectricity and room temperature in the strontium titanate, which is not ferroelectric? And so we see first is the reduced dimension with the emergence of the new phenomena, and by just using the existing nanopolar regions. But you can actually use this the strontium titanate ferroelectricity, and then is using the freedom and the new degree of freedom in the creating nanoelectronics. So easy to control the multiple nanoelectronics functions with the ferroelectricity. So for example, is strontium titanate is a very important material we know is 2D electron gas. And then when you get LaOSTO, and then very thin 2D electron gas formed. And then this also creating like a superconductivity, 2D superconductivity. And then this can be switched by the ferroelectricity strontium titanate, and you can have a modulate the 2D electron gas. So I like to summarize our talk is we actually use a design these nanopolar regions and create this emergence of ferroelectricity. And we demonstrate this one by PFM and then electrical measurement. Okay, I'd like to thank my group members, especially Dresselhaus is a driver of this project, and then other group members contributed to this project. Thank you very much.
Okay, got questions?
Sorry, maybe I missed the point about the calculations. When you create titanium defect in A position, anti-side position, It will be charge defect.
Oh, titanium is +2, not +4.
+2?
Yes.
Coexisting with +4 in B side?
This calculation is, I'm not the person who calculate this one, but it's a more stable configuration of the valence of this anti-site. It's not +4, +2, and then energy calculation based on +2, and then anti-site displacement 0.8 angstrom is based on that.
Okay, let's see.
I mean, I would think it might be possible there's other defects in there as well, other than just the anti-site. You know.
I think that's definitely possible, but you see that all the energy calculations of the point defects in the beginning of it, and then most probable defects is based on this calculation is the lowest energy, and then is an anti-site titanium site, this one. And you see that all other ones is positive energy, and then but this one is the most stable one.
Yeah, but I'm saying it could be coupled with other.
That's true.
defects.
That's true. Yeah, that's the one thing. Maybe some other point defect characterization is important.
Yeah, I don't know if people can hear you. So.
If I look to this table, the defect
Mm-hmm.
of anti-site titanium
Mhm.
holds charge +2, efficient charge, which means that formal charge is +4 in A side,
Mm-hmm.
and then you just build up global charge on the sample. It has to be compensated by something. If you just calculate the energy of this single defect, it makes no sense. It has to be associated with something else.
Okay, so this is a separate. This is not our calculation. This is a reference.
Yeah.
And then the charge calculation is done by Chef Shifan. I'm not the person who calculated Shifan. Actually, he left early, and then he might be the best person to answer what is the actual energy and then energy calculation.
Yeah, okay, one more question. Okay, I'll bring this over. Get some exercise.
Did you measure the transport properties of your pattern devices? You measure polarization with 24 unit cells. Did you measure transport with a top electrode?
You mean the what kind of transport measurement you're talking about?
An electroresistance?
Okay, that's what I show you. That's
With
the
the top
pond measurement. Pond measurement and then the TE measurement is done by top electrode, the strontium luthenate on top.
But
So
do
bottom electrode strontium
you,
luthenate.
yeah, I understand.
Yeah.
But did you measure the tunnel electroresistance with this top electrode?
Yes, we did. It's very similar to barium titanate.
Okay.
So we see that the tunnel resistance downstate, upstate, we see the very similar behavior like barium titanate.
Okay.
And thickness dependence is very similar. But actually, it only works at thin one because the tunneling works only thin regions. We cannot make a thick ones.
Okay, let's thank Professor Ohm again for that invited talk. Thank you. Thanks. So the next paper is by D. Amoroso on ab initio approach to structural, electronic, and ferroelectric properties of antimony sulfur iodide. Put it to full screen.
Yeah, yeah.
We hooked up to this.
Maybe I can try the
This is
laptop.
Oh. Anybody an expert on this?
Maybe I can try with another laptop.
Okay.
to work.
I think, what's the buttons you have to push on a PC to make things project? Oh, there'd be something just happened. There you go. I think I got it
Okay,
now.
okay.
Okay.
Some problem,
No, I think it'll
but no, because
There you go. Yep,
Okay.
right here.
okay. So good morning, everybody. I'm a PhD student of Philippe Gauset at the University of Liège, but I'm going to present the results coming from my master thesis with Silvia Picozzi at the University of L'Aquila. So the reason why we embarked on this research is to try to discover new material among this new class of ferroelectric relativistic semiconductors, and in particular these Rashba type multifunctional materials. Few studies has already been done about germanium telluride, but for sure the field needs to be consolidated. So in order to obtain such multifunctional materials, what is required is a possible coexistence of ferroelectricity and semiconductor character, and moreover a strong spin-Rb coupling that allows for the control of the spin degrees of freedom via an applied electric field. And so we found in the antimony sulfur iodide crystal a good candidate, and despite this crystal being fully characterized from an experimental point of view since many years, actually there are few poor characterization from the first principle point of view. And so we will provide here a comprehensive study about the structural, electronic, ferroelectric properties of this crystal, and then an interplay between these internal properties by means of an ab initio approach based on the standard on DFT within the bus package. So at first I need to recall some of the main physical concepts that we will find in our crystal that are for sure the well-known ferroelectricity, that means the presence of a permanent switchable polarization controllable via an applied electric field, but also a strong spin-Rb couplings that link the spin and lattice dynamics. So these allow for a fascinating interplay between the spin and the polar degrees of freedom. But what happens in detail in our system is that a particle in an electric field experiences of an internal magnetic field that couples with the spin. And so we need to add the so-called Rashba term in the Hamiltonian of the system. And so by resolving the eigenvalues relating to the Hamiltonian, we find linear spin splitting in the k-vector that resolve the degeneracy of the usual quadratic behavior of the energy itself. So what is important in order to observe this kind of phenomena are a presence of a time reversal symmetry, but a lack of the inversion symmetries. But historically, there are two ways to visualize these relativistic effects that are known as Rashba and Dresselhaus effects. And what is important to keep in mind at this moment is the behavior of the so-called spin texture. That means that the average of the spin in the k-space in the plane that is perpendicular to the polar axis. So within a Rashba effect, what happens is the spin texture is in each point tangential to the energy isosurface counter, Whereas within a Dresselhaus effect, we can find also radial component. And actually, it is possible to obtain coexistence of both these phenomena because they came from a specific atomic site asymmetry, so the asymmetries related to the point group, rather than the asymmetries related to the full crystal. Sorry. Okay, going inside the results, antimony sulfur iodide crystal count 12 atoms that are grouped in a parallel layer in the XY plane, and we can visualize the crystal as a quasi one-dimensional structure that is composed by zigzag chains that extend along the C crystallographic axis. And so this is a very asymmetric arrangement that is a rhombic pyramidal system. And moreover, it was suggested that the interaction between these two double chains are weak, like van der Waals type. From the space group point of view, so we have that the high symmetry reference, that is the paraelectric phase, belongs to the PN-HAM space group, whereas the polar phase belongs to the PN-A21 space group. And interesting is the Curie temperature that is about the room temperature. So from a structural point of view, we have that the phase transition is due to a relevant motion of the antimony and sulfur atoms that moves along the C direction, whereas the iodine is fixed. And so what happens is that this displacement causes an asymmetry in the arrangement of the antimony iodine and antimony sulfur bonds that produce the polarity of the crystal. And a first result came from the optimization, the relaxation of the ionic position, because by a standard approach, we are not able to reproduce the experimental ferroelectricity. That means that the displacement of both antimony and sulfur vanish, so that the paraelectric phase seems to be the stable one. Whereas by using an advanced approach by means of hybrid functional and, for instance, the HAC functional, we recover the ferroelectricity, and moreover, the values of both the displacement and also the main bond length are in very good agreement with the experimental data. So we can also characterize the compound from an electronic point of view. That means that looking at the density of states, and in particular to the projection of the orbital characters in the density of states, we can state that the S level of sulfur and iodine atoms are strongly localized in the lower part of the valence band, whereas an interesting mixing of characters is present in the upper part of the valence band. Indeed, this is the top of the valence band is characterized by the p states of sulfur and iodine, but also by an interesting amount of S states and p states of antimony. And then the conduction band is fully characterized by the p states of antimony and also p states of iodine and sulfur. That means that suggests that a strong sp hybridization is present in this compound. And as taking a look, by taking a look at the band structure, we can confirm that this crystal is an indirect gap semiconductor, and the top of the valence band is located along the XU line in the Brillouin zone, whereas the bottom of the conduction band is located at S point, and the value of the indirect gap amounts to 2.2 electron volt, whereas the lowest direct gap is located along the gamma Y direction, and it is about 2.3 electron volt. And also these values are comparable with the experimental data and suggest so the use of this compound in some photoferroic devices. As for the ferroelectric properties, as I mentioned, so the polarity is due to the motion of antimony and sulfur atoms, and in particular antimony shift of about 4% of the length of the C-axis. That is also the direction of the polarization. And these produce the formation of longer and shorter bonds that switch as a function of the polar mode. The calculated polarization, that is quite large, is a very good agreement with the experimental data, and from the FT calculation is about 20 microcoulomb per centimeter square. If we take a look to the trend of the energy as a function of the distortion, we can find the typical bistable energy profile that tells us that the ferroelectric phase is the ground state of the system, and the energy gain is about 6 millielectron volt per unit cell. So we can try also to justify the electronic bonding system by recalling the mixing of orbital characters in the density of the states, but also by taking a look to the values of the Born effective charge that indeed are very anomalous compared to the nominal values. That means that a strong covalency in the bond character is present, and so we can, again, talking about a SP hybridization model that occur between antimony and sulfur. So a simple model should be a first interaction between the field 5s state of antimony and the 3p states of sulfur, and then a second interaction between the antibonding levels and then the nominally empty 5p states of antimony. And moreover, this model should be confirmed by the presence in the top of the valence band of an active lone pair at the antimony site. It is important to notice that this is the same both for the paraelectric and the ferroelectric states, because the presence of this active lone pair is due to the strong asymmetries of the antimony site, and that is related to the bipyramidal arrangement of the chains. But if we look, the differences between the two phases is that the charge distribution is strongly affected by the polarity of the system, because, for instance, the lone pair tilt in the direction, in the opposite direction, comparing to the formation of the shorter bonds. That means it tilts in the opposite direction to where the displacement occurs. So, after this fully characterization, we started to look for interesting coupling phenomena, coupled phenomena, and so by put our attention on the conduction band, and in particular around the gamma point in the plane perpendicular to the z-axis, that means along the xy and ky and kx direction, we can see a typical inner-outer spin splitting of the band structure, and we can recognize in the behavior of the spin texture the coexistence of both the Dresselhaus and Rashba effect, because we can have both the radial and the tangential and radial components of the spin orientation. And we tried also to estimate the amount of the Rashba and Dresselhaus term by fitting our branches, and the result is that the Dresselhaus terms overcome a little bit the Rashba one, but they are both present. Moreover, if we perform with the same calculation on the reversed structure, that means on the structure that gives us the minus polarization, what happens is a typical spin switching in the direction of the spin texture itself. And this suggests so that it's possible to control the spin texture behavior as a function of the polarization. And so this is the result of the coupling between the ferroelectricity and these fascinating relativistic effects. And this behavior is called spin polarization. And so this is appealing for some spintronic devices, and it is important to notice that this crystal is not magnetic. So in the end, we provide a full characterization of this compound, and we confirm the possibility to use this in both photoferroic devices, because the amplitude of the value of the energy gap is in the visible spectrum. And moreover, we suggest interesting use of in spintronic devices because of this strong ferroelectricity that is present at a room temperature, so we can say at high temperature. And moreover, the value of the polarization is quite large. And we find out this coexistence of both the Rashba and Dresselhaus effect that allow for the control of the spin degrees freedom via an electric field. So I want to acknowledge all these people, in particular the people at the time within the Silvia Picozzi groups, and the organizer to give me the chance to give this talk, and everybody for their attention.
Thank you. I just want to say I really like this because it's actually the first ferroelectric I worked on in the 1980s, but it's way too complicated. So later on I moved to barium titanate and lead titanate, but giving up on this and never publishing anything. But it's very, very nice to see it worked out. Questions?
Yeah, thanks. The Rashba splitting is in your conduction band,
Yeah.
right? So that's empty states. Now, if you want to use that in spintronics, obviously you're going to have to populate them, which means pulling these states down below the Fermi level, presumably by doping or something.
Yeah, no,
but then if you do that, you've got density of states at the Fermi level, and will the ferroelectric state be stable, or will it be destabilized?
So actually, we try to look at the spin texture at the conduction band and around the gamma point, because we can see that the bands are well resolved there. Because another interesting point should be also the S point in the conduction band, and for sure to investigate the valence band. But at the moment, we focus just for the simplicity related to the symmetries, and so around this point in the conduction band. But for sure, it should be very interesting to investigate the behavior also in the valence band. What we did is to calculate also the effective, the all electron masses, just to take a look to the values, that if they should be, I have a slide about this. Here, yeah. And indeed, we have that in the valence band, if you look in the direction parallel to the polar axis and also along the KY, the value of the effective masses are interesting for possible application, I mean. So, yeah, but for sure is we should improve our investigation of all the spectra of the band structure.
When you switch the polarization,
Yeah.
then the spin switching is exact or only approximate?
No, exactly. Yeah. There is no correction. It's what happens by performing calculation on the reverse structure. Yeah.
I found that the switching barrier very small, and then that's very interesting. So have you also compared with the experimental, like a switching, like a voltage? And
No, from an experimental point of view, this kind of study, the spin texture and so on, are not, there are no work about this. So maybe we can find for some experimental people interesting too, because I know that it's possible to look at this spin splitting by some ARPES, something like this. But it's very difficult. Maybe if somebody is interested, we can go on.
Any other questions? Okay, thank you again. Thank you. The next paper is by Nowandnik, Ferroelectric Switching Pathways and Calcium-3 Titanate from first principles.
Do I need to?
Sometimes you need to close and open. Maybe you just make it go full screen. It might automatically. We're on the HDMI. I don't know if we need to do something.
I could try closing the laptop and reopening
Yeah,
it.
yeah.
Oh, there it is.
Yeah,
Okay. All right, thanks for the introduction, and I'd like to thank the organizers for the opportunity to give this talk. So today I'll be presenting some of our recent results on polarization switching in the hybrid improper ferroelectric, calcium titanate 327. So first I'd like to acknowledge my collaborators on this work, Andrew Mulder and Craig Feeney. I'm a postdoc in Craig's group. And we've heard several nice talks already in this conference on hybrid improper ferroelectrics and calcium titanate 327. So I'll just briefly remind you of these concepts. So first, hybrid improper ferroelectricity. Kind of the key thing I want to remind you of is in these systems, polarization can be induced via trilinear coupling in the free energy to two structural distortions, often octahedral rotations of different symmetry. And starting with the work of Bosque et al., there's been a lot of research in recent years into designing hybrid improper ferroelectrics and predicting materials that display this mechanism. And in particular, there's been predictions for hybrid improper ferroelectricity in AA prime ordered perovskite superlattices and in N=2 Redelston-Popper compounds. So why might one be interested in hybrid improper ferroelectrics? I'd like to highlight two main reasons. The first is that octahedral rotations couple to many materials' properties, such as bandwidth and metal insulator transitions and magnetism. And so coupling a polarization to octahedral rotations, and hence those properties, offers the possibility to control those properties with an electric field and potentially new functional materials. Secondly, octahedral rotations are ubiquitous in perovskite oxides, so ferroelectricity induced by those octahedral rotations should in principle be possible in a wide range of chemistries. So with that introduction, I'm going to focus now on the hybrid improper ferroelectric, which is the focus of this talk, calcium titanate 327. This is a N=2 Redelston-Popper compound, which means there are perovskite slabs of thickness 2 separated by a rock salt layer. And at room temperature, this crystallizes in an orthorhombic polar space group, A21AM, shown over here on the right, which is significantly distorted from the high symmetry prototype I4 MMM. And so this distorted structure can be decomposed into three distortions. there's two octahedral rotations. One is an out-of-phase tilt pattern about the 110 axis, which transforms like the IRUP X3 minus. So I'll be labeling it that way throughout this talk. The second is an in-phase octahedral rotation about 001, which is transformed as X2 plus. And these two octahedral rotations couple trilinearly in the free energy to a polar mode, which has polar displacements along 110. And this paper down here on the right therefore predicted ferroelectricity in this system via this trilinear coupling mechanism. And then in a very exciting result in the last year, ferroelectricity was demonstrated in this material in Sungwook Shung's group. So here, we've already seen these results earlier in the week, but here on the left is a hysteresis loop demonstrating a switchable polarization so that this system is ferroelectric. And then the question is the mechanism for ferroelectricity in this system a hybrid and proper mechanism? So over here are some XRD results showing the temperature evolution of the amplitude of the two octahedral rotation modes in the top and the polarization in the bottom. And these all evolve with temperature proportional to one another, as one would expect in a trilinear coupling mechanism. In addition, the temperature dependence of the polarization is linear in temperature, so it's improper-like, which is significant. There's other trilinearly coupled ferroelectrics, such as the Arrhenius phases, that are more proper-like. So this brings me to the main focus of this talk, which is thinking about polarization switching in calcium titanate 327. So since polarization switching is a very complex topic, I need to tell you how we're going to approach it. So we'll be using some group theory and first principles calculations to look at intrinsic energy barriers for polarization switching in this system. And specifically, we'll be looking at the two-dimensional order parameters, x3 minus and x2 plus for these octahedral rotations. These are formerly two-dimensional quantities, although some previous works have treated them one-dimensionally. And so you can think of these order parameters now as like a vector in a two-dimensional order parameter space. And such an approach has been used previously to study switching in bismuth ferrite, lanthanum ferrite superlattices. So the main outline for this talk is we're going to start with a fairly abstract approach and look at all of the structures we can form by combining these two order parameters and their energetics. Then we'll use that sort of overview of possible structures to enumerate switching pathways and look at their barriers. And then at the end, I'll tell you that we'll get some results that are actually very relevant for switching in the real material. So let's start out by looking at these two-dimensional order parameters. So here's x3 minus. This is the octahedral tilting mode. And depending on the direction and order parameter space, we can, now that we're working in two dimensions, we form different subgroups of I4MMM. So here I'm showing the direction and order parameter space, also shown in this picture, the space group, and then the energy of calcium titanate 327 when I relax it in that structure within VASP. And then down here is just what that structure looks like. So in a lot of the rest of this talk, I'll be working in this order parameter notation because it's sort of the most efficient way to enumerate these different switching pathways. But keep in mind that you can always map this order parameter picture onto a real crystallographic structure. So we see these different space groups, and there's, in this case, there's these two different structures which have pretty similar energies. We can do the same for the x2 plus octahedral rotation order parameter, also list out the space groups and look at their energies. So now let's look at all of the subgroups we can get by combining these two order parameters. Here they are. So here's the directions and order parameter space, the space group labels, and then their energy. The 0 here I'm setting to the energy of the ferroelectric ground state, A21AM. The key thing to notice is that we find a very low energy structure, PNMA, not to be confused with the perovskite PNMA. I'll talk about this more later. And then we find a number of structures that are kind of in the 30 to 40 MeV energy range. So now let's use this overview of structures to look at potential switching pathways. So this trilinear term in the free energy has important implications for switching. Namely, if we want to switch P, so take P to minus P, we need to reverse the sense of one but not both of the octahedral rotations. So that means if we have a rotation that's initially going like clockwise, it will then be going counterclockwise after the switching. So say this is our initial state. We have this polarization, and these are the what these two octahedral rotation order parameters look like. If we want to switch the polarization, we're going to either need to switch the x3 order parameter or the x2 order parameter. So these are the two final state structures we could get to with a reversed polarization. So there's different ways we can do that. Some of them have been considered before that treated these order parameters as one-dimensional. In that case, you can either turn off the x3 order parameter and turn it back on in the opposite direction, or you can do that with the x2 order parameter. But now that we're working with two-dimensional order parameters, there's more possibilities. So for example, we could consider rotating the x2 order parameter instead of turning it on and off, or similarly rotating x3. And finally, the last possibility is we can consider rotating both order parameters at the same time, and then continuing to rotate one while rotating the other one back to get to this switch state. So this all corresponds to real changes in the crystallographic structure. I'm just drawing an order parameter space here. And so that's it. So restricting to this space defined by these x3 and x2 order parameters, these were all of the different ways to go to this reversed polarization state in 2 steps or less. So now let's look at what are the energy barriers for switching via these pathways. So I'll start with the one-dimensional pathways, which were considered before. Here I'm just reproducing what the order parameters look like during the switching. Down here I'm showing the energy as a function of a switching coordinate. So we obtain this energy barrier of 56 MeV by turning off the octahedral rotation and turning it back on. We can do the same thing, and we can do the same thing for the switching the octahedral tilt mode. So keep these numbers in mind to compare to some of our other switching pathways we're now going to consider. So now let's look at the pathway where we consider rotating the x2 order parameter. Here I've labeled the space groups and directions of these different structures, and these came from this table we had previously made. And down here's the energy as a function of switching coordinate. Now it has a lower energy barrier, 32 MeV per titanium, and it's a 2-step process, meaning it's going through this barrier twice. And in the middle here, we find this structure PNMA, which is this very low energy structure, very close to the ferroelectric ground state energy. So let's take a closer look at what this is. On the left here, I'm showing A21AM, the ground state. And because it's ferroelectric, 2 adjacent slabs have polarizations pointing in the same direction. Over here, I'm showing PNMA. This is antipolar, so 2 adjacent slabs have polarizations pointing in opposite directions. And now if we look down at these 2 adjacent slabs from the top, because you can see here that the x3 tilt order parameter in red is the same in both of these structures, but the x2 order parameter in green, so that's the octahedral rotations, is different. And so here, if you look at these black arrows, in slab 1, these have the same sense of rotation, but in slab 2, the sense of the rotations is different. So the only difference between these structures is the sense of these x2 rotations in one slab. That's a pretty small difference, so that's why they're so close in energy. And now let's finally look at this switching pathway where we rotate both of the order parameters. Again, I've labeled the space groups that were from this table, and here's the energy as a function of switching coordinate. Again, it's a 2-step pathway, and it's a fairly low energy barrier. And here in the middle, what's this structure? This is BB21M, which is the orthorhombic twin, since this is an orthorhombic space group. So this is relevant for switching via an orthorhombic twin domain. So let's look a little more carefully at that. Here I'm just showing a top view of one of these perovskite slabs that goes into the RP structure. And so here we're in twin A, then we're in twin B, and back in twin A with the polarization reversed. And you can see what happens is the polarization and the tilt axis for the X3 mode, which is shown by this dashed line, they rotate during the switching process. So here, in the starting and ending configurations, if you look at these red arrows, the sense of this tilt mode has changed, but we didn't ever turn it on and off. We just we rotated the tilt axis. So this is the summary of the energetics of these different switching paths we considered. By looking at these two-dimensional order parameters, we identified some new low-energy paths. And now I'm going to, in the last couple of minutes, just briefly tell you how this is relevant for real switching in calcium titanate 327. So let's start out by looking at the crystallographic structure again. Here I'm just showing a supercell of calcium titanate 327 for illustration. I didn't perform calculations in this cell. And so, we have these perovskite slabs that are stacked on top of each other, and they're weakly connected along the z direction. And because this is, if we're in the ferroelectric state, then in a polar state, then all of the polarization in all slabs is pointing in the same direction. But we could also imagine having some kind of configuration, because these slabs are weakly connected along z, where there's like a stacking domain that happens at some point here. And so on the bottom we have polarization going to the right, on the top we have polarization going to the left. And then we could imagine switching the polarization by moving this stacking domain. So now if we just zoom in on this region here where this domain moved, we can see this is the antipolar structure PNMA I introduced before, and then this is the polar ground state structure. And so switching from this state to this state is exactly this second half of the switching path I showed before. So if we already have these stacking domains in the material, it's actually just a one-step path to go between these. And now finally, the other sort of key structural feature to consider are the orthorhombic twin domains. These were observed in the experiments in Sung-Wook Jung's group using optical techniques over here. And then on the right, they used PFM to map out the ferroelectric domains. They find that the ferroelectric and ferroelastic domains line up as one would expect in a trilinearly coupled ferroelectric. And they have a very nice discussion in their paper about how this abundance of these domains lead to the orthorhombic twins being likely key for switching. And so just to sort of draw a schematic of that, suppose we have some domain wall here in this purple line, and these red arrows are denoting how the octahedra are tilting. We could imagine a switching process where if you focus just on this octahedra here, where it can change its tilt by 90 degrees relatively. So of course the real switching would involve domain wall motion, but this is kind of a schematic picture. And so this kind of process would correspond to this switching process we looked at. So that brings me to the end of this talk. The main conclusion is we considered these order parameters. We carefully considered the two-dimensional order parameters, and we found some low-energy switching pathways which are relevant for calcium titanate 327 and the domains that are present there. And we did some additional work on understanding how the order parameters evolve, during the switching process, which I'd be happy to talk to you later if you're interested. Thank you.
Time for questions. Did you look at the domain wall energy?
No, so we were just looking at these intrinsic energy barriers with the DFT calculation.
Okay.
It seems that the coercive field is very large for a material with small polarization. Am I right?
So
If I think in one slide you showed a hysteresis loop, the corrosive field is very large, right? Much larger than even single crystal PTO. But this system, I think, has small polarization.
Yeah, I mean, I guess with these calculations, I can't exactly comment on the corrosive field, but I mean, with these results, we found these relatively low energy switching pathways. But of course, like, yeah, the intrinsic barriers would be, are related in some way to the corrosive field.
Yeah. Wait.
I think the connection between the size of the polarization and the corrosive field is very different and improper. This is an improper ferroelectric versus a proper. I'm not sure exactly how it would go, but I think it's very different. So.
Okay, let's thank the speaker again. Thank you. The next talk is by M. Ito on shearing-mediated ferroelectricity, polarization switching caused by the bond recombination of cations. Yeah, that's the best is to use. Thank you. And then, use the microphone also.
Thank you for Chairman. And first of all, I'd like to express my sincere thanks to the organizing committee members and to give a chance to talk about our recent study. Anyway, I'm Ito from Tokyo Institute of Technology, and these people are collaborators for this project. And today, I will talk about tetrahedral ferroelectric. And this is not perovskite, was a material. And so maybe such a research may be new for you. And this is outlined. First, I will talk about the motivation for the tetrahedral, searching for the ferroelectric material. Next, I will talk about the crystal structure of the kappa alumina. And next, sample preparation and measurement of P loop and ab initio calculation for the polarization and the polarization switching. And finally, conclude. And 5 years ago, our group has begun the project for the searching for the new material in the tetrahedral ferroelectric. And this is the first example of the tetrahedral ferroelectric. And you are familiar with this material. And this is an all-reduced compound. And this is famous for the ferroelectric. And when this material contains bismuth 2 tungsten 06. And when you replace the tungsten by silicon, this material turns into bismuth 2 SiO5. And but after the replacement, the framework of the structure is maintained. So this is the AX view of the two structures. And this is the bismuth tungstate, and this is bismuth silicate. And you can see that the structure of the fluoride layer is maintained. And the only difference is change from the tungsten 06 octahedral to SiO4 chain. But in this case, the linear chain of the SiO4 appears. And this is only the difference between the two structures. And And the detail was published 3 years ago by Professor Taniguchi. He is now in Nagoya University in Japan. Anyway, this material shows ferroelectric transition temperature at around 673. And you can see the peak top in the direct measurement or a P loop. And the important information is that this material has a ferroelectric soft mode like this. And this figure shows that temperature dependence of the ferroelectric frequency of the ferroelectric soft mode. And secondly, the important results were conducted from the initial calculation, both for high temperature phase of the paraelectric phase, CM. And the second one is for the CC phase. This is ferroelectric phase. And the important information is that the paraelectric phase has a soft mode like this. And this is consistent with the Raman data. Also, thirdly, the important information was obtained from the calculation for polarization switching. And the polarization switching, during the polarization switching from up to down, the intermediate state was taken as a CM. So in this case, the activation energy, polarization switching energy was calculated to be 0.22 electron volt per formula unit. And also the polarization is fairly large compared, and this is comparable to that of the barium titanate. And this is secondly, we have calculated the possibility of the Urside. No one believes that this is pyroelectric, and many people believe that this Urside structure cannot be the polarization in the Urside structure cannot be switched. But as far as we have calculated the polarization for this trigon bipyramid, and when we move the cations from the center of the bottom tetrahedra to upper tetrahedra, the activation energy for the switching is obtained to be 0.2 electron volt to 0.3 electron volt for beryllium oxide. And in 1972, Professor Shozo Sawada has measured the dielectric P loop for beryllium oxide single crystal. And he has obtained the ferroelectric-like P loop for beryllium oxide. Anyway, this is and the result was published by Dr. Moriwake in 2 years ago. So this is just a summary of recent research. And so next strategy was to get to use both tetrahedra and octahedra. And so I am chemist, so we have searched for about 700 compounds referring to the papers. And so one of the candidates was alumina. And because as you know that alumina, hydroxide alumina, decomposes into alpha alumina finally at high temperatures. And during the decomposition process, there are many kinds of intermediate phase, metastable phase of about 12. And above, among the intermediate metastable phases, only kappa and kappa prime alumina has a non-central symmetric space group. And so these two materials, only two materials are pyroelectric. So we have begun this study. And before going to the detail of the experimental result, I should explain the structure of the kappa alumina. And the kappa alumina and the epsilon gallate or epsilon ferrite also take the same structure with the kappa alumina. And recently, the researches for this material is carried out by many researchers. Anyway, the characteristic of the alumina system is oxygen closed packing. So, for example, if we look at the corundum structure, the oxygen closed packing layer sequence is given by AB, like this. And also, in the case of the spinel or spinel-related structure, we can see that the sequence is ABC. And in the case of, if we look at the kappa alumina structure like this, the oxygen closed-packed layer sequence is given by ACAB. And this is a characteristic of this structure. So we can say that this kappa alumina structure is composed of corundum and spinel. This is the compromise of two structures. So anyway, this is the explanation for the structure. And as far as I know, the compound with the kappa alumina structure is given like this. And the last three compounds was recently synthesized by our group. And this is again the explanation for the structure of the kappa alumina. And you can see that this is a corundum and this is a spinel. And the corundum structure, as you know, that this is composed of only octahedra. And the spinel structure composed of octahedra and tetrahedra. So, and the mixture of the two structures are kappa alumina structure. And this is the explanation for the structure. And this is experimental. And we have fabricated these 5 compounds. All of them have the kappa alumina structure. And the thin film was fabricated by PLD. And thickness of the film was 10 to 100 nanometer. And substrate was always used Niobu STO 111 surface. And the structure analysis was carried out using the X-ray and TEM. And P-loop was measured by a conventional method and the pound. And this is one of the example of the structure of the thin film. This is the case for gallium ferrite. And this is a substrate, STO111. And this is the film of the gallium ferrite. And you can see that the calculated structure agrees with the observed one. And the other characteristic is that in this system has 3 domains, and domain 1 to 3. And this is coming from the STO111 structure, because the STO111 structure has 3-fold symmetry. So the deposited film may tend to have 3 domains like this. And this is a summary for the P-loop measurement for all the compounds. And only the gallium compound was measured by using the pound due to the very large leakage current. So anyway, from the aluminium to indium, maybe these materials we can say that these materials are ferroelectric. So after obtaining these results, we have carried out ab initio calculation for this material. And also the and this is the explanation for the polarization switching mechanism. And the non-central symmetric PNA21, yeah, this is downward polarization, and this is upward polarization. And we have used the non-central symmetric, central symmetric intermediate phase state was PBCN structure. And using this assumption, we could obtain the result of the for the activation energy for the switching. And in the case of the kappa alumina, and this is about 0.15. And both epsilon ferrite and epsilon gallate case, and the energy was found to be 0.09 electron volt. And maybe this is fairly small than expected. Anyway, and this is the structural change during the polarization switching, viewing from the A-axis. And as you can see that this is the corundum layer, and this is the spinel layer. And when the polarization switching occurs, this tetrahedra tie into octahedra, and this octahedra tie into tetrahedra. And this is polarization switching. And the other one is that a different view from the B-axis view. And in this case, very different information is obtained. And the corundum layer and the spinel layer is same, but in this case, in this direction, the cross-packed layer of the oxygen is shifting each other. So this is sharing, kind of sharing. So this kind of sharing may induce the recombination of the tetrahedra to octahedron, or octahedra to tetrahedra. And maybe this is a polarization switching mechanism in kappa alumina. And in the last I will talk about the difference between the previous model, and that was reported by Stepler in 2012 for gallium ferrite. And in his model, the intermediate phase was used, PNNA. And in this case, the polarization switching occurs in this tetrahedra and octahedra, both in spinel layer and corundum layer. And in this case, the activation energy is calculated at around 0.5 electron volt. But in our model, we use PBCN for like this. And in this case, the activation energy is decreased down to 0.1 electron volt. So this is a summary for the kappa alumina type oxide. And there are many kinds of the kappa alumina type compounds, ABO3, and including the Sasaki oxide. Anyway, maybe the intermediate phase during the polarization switching maybe the PBCN. And the calculated polarization is 26 or 21 for this material. But there is one problem. The experimentally, the polarization value is 1 to 3 microcoulomb per square centimeters. And this is one order smaller than the calculated value. And also, we have calculated the activation energy for this material. And this is maybe around 0.1 electron volt or something. And the present problem is to solve the difference between the calculated value of the polarization, calculated values of the polarization based on the calculated and experimental. And this is the summary for the result. And we could prepare the five kinds of the copper alumina type compounds. And these material, all these materials show the ferroelectricity. And so the detailed discussion will be reported in the near future. So thank you very much.
Thank you for an interesting talk. So how much strain is associated with the change in polarization? Obviously, in the photograph you showed of the switching process, it looked like there was a lot of strain involved. Is that how much strain is involved in the change in polarization? You know, like it looks, these are all remaining orthorhombic, but it seemed like there's a significant change in the lattice constants.
Oh, sorry, I have forgotten the detail.
Okay.
Yeah, sorry.
It's known that epsilon phase of iron oxide is ferrimagnet up to 500 Kelvin, and it's ferroelectric as well, above room temperature. So it's a multiferroic above room temperature.
Yeah.
How is it with your compounds, scandium ferrite and gallium ferrite and other? Is it something known about magnetic properties?
Yeah. Basically, these material, all these material shows very magnetic, and but the Tn changes depending on the composition. Yeah. And the highest one is for the Indian.
Is it always above room temperature?
Yeah. Around 380. And the lowest one is aluminum ferrite. And the Tn, but exactly the Tn, but the Tn is around 150. So depending on the size of the A-site ion, the Tn changes. And so there is a other multiferroelectricity. We need the insulate thin film, and also we should, for example, control the direction of the polarization, magnetic polarization perpendicularly. So now we are doing such a.
Any other questions? Okay.
Do you know roughly the polarization quantum for this system?
Pardon?
Do you know what the polarization quantum is for your system?
Quantum?
So the quantum of polarization, so the formal value you calculate is only well-defined modulo this quantum, and if you don't know it, that's fine.
But it may be
right, that's what my thoughts were.
So when you calculate the polarization, it's plus or minus. It's like on a lattice. So it could be that you're not looking at the one that corresponds to the experimental, the smallest. So that might be the reason for the difference there, possibly, or it could be some material issue. Okay. Thank you, speaker again. Thank you. Okay, the next talk is by M. Yen on ferroelectricity in corundum fluids. Should stick around for the suspense of the prize announcements. Okay, good.
You got the microphone. You need to.
Okay, hello everyone. My name is Meng Ye. I'm from Rutgers University. I would like to thank the organizer to give me the chance to talk about my recent work on ferroelectricity in current and derivatives. So what is the motivation? So we know that lithium niobate is a ferroelectric material with very large spontaneous polarization. So why can't we find more ferroelectric materials in this family? So actually recently a lot of materials has been synthesized in this current and derivative family at Rutgers University Green-Glass group trying to find more ferroelectric materials. And our purpose is use first principle calculations to trying to calculate this polarization reversal path and barrier. And in the following, I will show the structure of current and derivatives, and then I will use lithium niobate as an example to explain the mechanisms, and then we'll show you the result from our calculation, the coherent ferroelectric barrier and the domain wall mediated ferroelectric barrier. Okay, so here is the current and derivative structure. I should thank the previous speaker because he already showed the structure. So this is the current structure, but with cation ordering. So those four can be different cations. Each one is in an oxygen octahedral environment. When those four cations are the same, it's the current structure, but in general, you can add different cations to make this material. And this is the top view of this material. So this oxygen octahedron forms a hexagonal lattice. So then let's look at lithium niobate. So lithium niobate has the same structure. So lithium niobate like AB, AB. It has a very huge spontaneous polarization. And this are the ferroelectric phases with opposite polarization. And this is the paraelectric phase, and its average structure is like this. So the lithium atoms is in the plane with the oxygen, but it's just the average structure. So if we look from left all the way to the right to see how the polarization changes, we can see that basically the polarization changes as the lithium, these two lithium cations, move downward, move across this oxygen plane and to this oxygen octahedra beneath it. So if we assume for all the current and derivatives, this mechanism works, then let's play with this structure. So this is the general current and derivative structure. Let's move these two cations downward, and we got this one. If we assume it is ferroelectric, and we assume that these two structures are related by inversion symmetry, so one is P, another is minus P, then how could these two be the same material? So the only possibility is either this yellow is equal to the green, or the purple is equal to the blue, as shown here. So when both those conditions are satisfied, then we have this lithium niobate structure, this AB, AB. If only one of these conditions is satisfied, then we have this AB, AB prime structure. So here what we learn is, under this assumption, if those two are related by inversion symmetry, then we can only this LNO type and this ordered LNO type can possibly be ferroelectric, and then we will study these two kind of structure. And here are those materials that we studied. For the LNO type, we include lithium niobate, lithium tantalum. They are already known ferroelectric, and a lot of those materials actually has been synthesized. So our goal is to reverse the polarization in those materials and find the energy barrier. And the energy barriers that we calculate has two types. One is the coherent or intrinsic type. that we have only one single domain, and we flip the polarization in all the unit cell. And we also consider the case with multi-domains, so we have domain wall. When a field is applied, one of the polarization domain will expand, so the domain wall will move. And let's first, and here are those calculation details. And we have a relatively large unit cell for the domain wall calculation. Let's first look at the coherent barrier. So we know that, for example, taking lithium niobate as example. So we know that the small A cations like lithium need to move downward. So we define these two distances, C1 and C2, and we plot it in this parameter space. So at the ground state, those two are the same, so they are on the diagonal line with high symmetry R3C. And then we're gonna use this as a structure constraint, and we gradually change this value so that these two A cations move gradually downward. And this point will slowly move from here all the way here. But our only constraint is this structural constraint. And okay, we changed constraint now. We see here, at the beginning of the structure, the two lithium atoms move together and they stay on the high symmetry path. But starting somewhere here, this path deviates from the R3C, which means that these two lithium atoms doesn't move together. So one of them, in this case, is the A2 cation that first penetrates the oxygen plane. And the reason we have these two lines is because these two A cations are equivalent, so one of them can move first, showing on this line. Okay, keep going. So this is when the constraint is equal to 0, when C1 plus C2 is equal to 0, and the point is here. So what's interesting here is this structure has R3 bar symmetry, but the ferroelectric phase, which I show you that this A cation is in the oxygen plane, is here, is at this R3 bar C symmetry. So what we found is that the midpoint structure of this ferroelectric reversal in the ferroelectric reversal path is different from the ferroelectric phase. And by moving from here to here, the energy barrier gets lower. Okay, and now the A1 cation moved downward. And now we are at the structure where the polarization is reversed. So a summary, we're going from the red top all the way to the left bottom, driven by an unstable polar mode. But starting here, there is an unstable nonpolar mode that makes these two A cations move one first, another follows. That's why we have this bubble inside, and that's why the energy barrier is lower here. And for the older LNO type, we get similar curves, except that at the starting point, it has a lower symmetry, so it's not on this diagonal line. This is a summary of our numerical result, and those are the structures we calculate. So if we use lithium niobate as for comparison, then a lot of them has energy barriers that's comparable or even smaller than lithium niobate, and they all have very large spontaneous polarization. And here this UDU, that is the magnetic state, because here we have magnet or iron. And this is the energy barrier, what's the energy, how the energy changes along the path. And you see, for most of the curves, the energy, the maximum energy is at when the constraint is equal to 0. That corresponding to this structure, this midpoint structure. And now let's switch gears, and I want to talk about the domain wall-mediated ferroelectric reversal. So when a domain expands, let's look at this figure. So I have a domain wall here. We only need to flip the polarization close to the domain wall, and in this, and so that the domain will move one step to the right on this figure. So this is what we do in the calculation. We only flip the polarization close to the domain wall. And when we construct the domain wall, we also notice that because this structure has threefold symmetry, so there are two different types of domain wall depending on the direction of this domain wall, X and Y type. And in all our calculation, we find this Y-type domain wall has a lower energy. So in the following, all our result, all the barriers will be for this Y-type domain wall. And this is a schematic showing how we flip the polarization. So we use the same strategy. We constrain this C1, we have the same structure constraint, and we flip the polarization to calculate the barrier. And we can also calculate the domain wall formation energy. But here, there is a small problem. So when because we have periodic boundary conditions, so we always have two domains, one between up-down, another between down-up. For the ordered LNO case, because this B and B prime are not the same, so the symmetry is lower, then the two domain walls are not the same. So we can only estimate the average energy of this two domain wall for this material. And here are the results. So we calculate these materials, and we find that the energy barriers reduce significantly. And here is what the energy look like along the path. The energy barrier is not at this 0 point. It's here, corresponding to the structure that when only one of the A cations trying to go through this oxygen plane. And here I highlight some of the materials that has a lower energy barrier. All of this, we got a very low energy barrier, but it's relatively difficult to calculate domain wall. So is there any other way we can estimate the domain wall barrier before we do the calculation? Here, the ferroelectric polarization switching is majorly driven by this A cation moving all the way from here to here. So if this A cation is loosely bounded to the environment, then you can imagine it can easily move a long way. So we find that if we use the band valence sum as our empirical parameter, so this R is the band length between the A cation and the oxygen cage. And Ri and B are empirical parameters. So in this x-axis, if the band valence is smaller than 1, it means the A cation is loosely bounded to the environment. If it's larger than 1, it's overbounded to the environment. And we find that there is a linear correlation between the band valence and the domain wall energy. And by the way, this band valence sum are calculated from the ground state. So we don't need to, if you have the X-ray data, if you know the structure, you can estimate the domain wall barrier. Okay, here is the summary. So those are all the results we calculate. If we compare these two columns, we see that the domain wall barrier is much lower than the coherent barrier. And here are the materials that has lower barrier in both cases. And for this iron titanium and this magnet iron tungsten materials, I put a star here because we find in the calculation the switching path becomes conducting. But so the path is more subtle, that need more research on it. And in the summary, we developed methods to calculate the incoherent barrier and the domain wall barrier. And we found several new materials that could possibly be new ferroelectric. And we find that the band valence sum is a good measure to help us discover new ferroelectric materials in current and derivative families. Thank you all for your attention.
Thank you. Just a quick comment. So what's the middle of your triple well? What is the structure there?
In this case?
Yes.
So the middle is the one, the middle is like this structure.
Okay.
But it's not the one that with the highest barrier, because when we have the domain wall, the oxygen can expand.
Well, the interesting thing about this was this big controversy. Maybe you know about it, but Glass had this model from experiments for a triple well structure for these materials. And we thought we disproved that with our double well, but actually I see this triple well again. So anyway, that's interesting. So one thing, though, is that the actual cohesive field is not exactly, I mean, you're moving the boundary one step, right?
Yeah, for the domain war.
Whereas the energy, I mean, it's not exactly equivalent, whereas the homogeneous switching energy is for switching the whole structure.
Yeah.
So neither of them are exactly what you would see in an experiment, right?
Yeah, exactly.
I think. Questions?
So depending on like which atom you choose at the A side, I think there might be like two kinds of high symmetric structure. I mean, lithium niobate is well known, and the high symmetric structure of lithium niobate has the lithium in the plane of the oxygen. So for other material, like which kind of high symmetrics you choose for the,
I see. So okay, let me see whether I got your question correctly. So you mean like for lithium niobate, this is niobium, these two are lithium, there's no ambiguity. But if I have this A2BB prime, this can be either B or B prime. Is that the question?
Yeah, I mean, like, take lithium niobate as an example. I mean, it's possible that niobate can be in the plane of the oxygen.
So you think B cations may be the one that move?
Right. So you have to choose which one is the A side.
Okay. Yeah, so in these materials, as I showed, I always talk about the moving one is the A cations. I think it's with the convention that they define the one with the smaller one, or the one with small valence charge, is the A cation. And that is, in all the calculations, it is the A cation that is moving. So it's kind of like the definition. You can always define the one that is moving as the A cation.
Okay, I see. Thank you.
Yeah, and I should clarify what I just said about Glass's model, because that was for the the thermal, ferroelectric to paraelectric phase transition. So I guess the question, so you're looking at switching process at essentially zero temperature. What do you think happens at the ferroelectric phase transition at high temperature?
So for this, for example, lithium niobate example, it's an older disorder type, right? So in that sense, I think it's not like this kind of switching.
So maybe more like a double well picture, not triple well when you look at the thermal transition.
Yeah, that's possible.
Any other, one more question? Okay, let's thank speaker again. So we move to the final talk of our session and meeting, and then afterwards excitement is building towards the awarding of the prizes. So stick around. And in case we forget to mention at the end, on the desk downstairs there are participant lists, so you can take one of those. I guess we shouldn't put it on the website. Maybe everyone doesn't want to get all the spam associated with their email address being on the website. Just pick up a participant list if you want to have the names and email addresses of everyone that's here. The next talk is Nahas on underlying topological features in ferroelectrics. Okay, good. Oh, please take the mic.
So, hello everyone. My name is Nahas, and on a closing note, I'll be discussing some underlying topological features in ferroelectrics, particularly focusing on an intermediate BKT phase for which we have gathered some evidence in ferroelectric thin films. So I'd like to thank the organizers for giving me the opportunity to discuss these results here. And I'd also like to acknowledge and thank Sergei Prokhorenko, Igor Kornev, and Laurent Belèche. So first, just a few general words about the BKT phase transition. So usually the critical behavior is conditioned by the dimensionality of the system and by the symmetry of the order parameter. So it happens that in 2 dimensions, for systems with a continuous symmetry, as it is best captured by the 2D XY model, fluctuations prevent the breaking of the symmetry. So one does not see any spontaneous symmetry breaking, and one should not expect any long-range order at low temperatures. So this is established within the Merman-Wagner theorem. However, although we are not in presence of the common phase transitions, we have a phase transition of another kind, of a topological kind, that can occur. And this type of transitions has been established since the early 70s by Berezinski, then Kostelis and Toules. And it has greatly impacted various areas of physics for its ability to describe various 2-dimensional phenomena such as superfluidity, superconductivity, some also liquid crystals and polymer films, and so on. More than thousands of papers on the application of BKT. But so far, to the best of our knowledge, this BKT transition has not been reported in ferroelectrics. So the main features of the BKT transition that we'll go through them later because they will serve us as a guideline for proving this emergence of a critical phase, are that this BKT transition is a transition of infinite order. It means that the free energy and all its derivatives behave continuously. However, above TBKT, so TBKT stands for the critical temperature for such transition, the role played by topological defects is predominant. It is their binding into pairs that allows the correlation of the order parameter to decay only with a power law behavior, which means that there is a certain stiffness in the system. And moreover, this power law behavior, so 1 over r to the power of nu, where nu is the critical exponent characterizing the decay of the 2-point correlation function, is a temperature-dependent critical exponent. So it means that below TBKT, all through the BKT phase, one can regard the system as consisting of a line of critical points. Each temperature below TBKT is a critical temperature. Above TBKT, those paired topological defects start to dissociate, and their disordering strength is enhanced, and also they proliferate in number, which causes the correlation function to decay exponentially in distance, which is typical of a short-range disordered phase. So, however, there is an essential singularity in the behavior of the correlation length, since upon approaching TBKT from above, it diverges exponentially, which means that the nu, the critical exponent characterizing the correlation length, should be equal to infinity. So, all this occurs for continuous symmetries. So why discuss ferroelectrics then? At first sight, ferroelectrics, who have discrete symmetry that combine the cubic anisotropy of the underlying crystalline structure and the ferroelectric interactions, should be left out from this type of consideration. However, there have been major works about the arousal of continuous symmetry as an emergent, non-exact symmetry of the Hamiltonian, which then can underpin the occurrence of a BKT transition. So the aim was to assess whether the BKT phase would remain stable against the introduction of anisotropy in ferroelectric thin films. So to remain as close as possible to the settings of the 2-dimensional XY model, so the paradigmatical model that captures the BKT transition, we have opted for a thin film, rather very thin, about 12 angstrom thickness, and we have tensilely strained it 3%. And this morphology allows the system to be regarded as quasi 2-dimensional And the order parameter, so the local dipole moments, the polarization, has two essential components, the Ux and Uy. So it is confined to lie within the film plane and is free to rotate within it. And this is, for instance, shown in the distribution of local dipole components, where we see that the Z component is a Gaussian centered on 0. So we have performed Monte Carlo simulations as well as molecular dynamics simulations using the effective Hamiltonian scheme. And we have considered several lateral sizes of our system. So preliminarily, we had to assess the order of the phase transition taking to the long-range ferroelectric order. And for that, we have performed some Wang-Landau algorithm-based simulations that enables to assess the structure of the free energy with respect to the internal energy. And we find that the structure remains with a single well at and around criticality, which confirms the continuous order of this phase transition, and which, most importantly, enables us to perform finite size scaling analysis, since such analysis is based on the divergence of the correlation length. So one of the major tools that are usually resorted to in order to probe criticality and to locate critical points is the so-called Binder cumulant, which is a fourth-order cumulant that captures the fluctuations of the order parameter. So the key role of such an observable is to become size independent as one reaches criticality. And hence, for a second-order common continuous phase transition, a family of Binder cumulant curves should cross at the critical point, while for the BKT phase, which is, I remind you, a phase of critical points, they should cross over an extended range, which means that they should overlap. And we have calculated such a quantity for 4 different lateral sizes of the supercell, and you can already see that there is indeed a crossing point occurring at about 540 Kelvin. And this crossing is followed by what seems to be an overlap within the error bars of this Binder quantity. So this is a first hint pointing towards the direction of the occurrence of intermediate BKT phase between the low temperature ordered ferroelectric state and the disordered phase above. So to more accurately determine such existence of the BKT transition, one can look at the Binder versus Binder type of curve. So this type of curves are interesting because they are linked, their slope is linked to the critical exponent nu, which in the case of a BKT transition should be infinite. So we have computed this for several pairs of sizes, and here we show, for instance, Binder for size 26 versus 24, and you see that at low temperature the data makes a bump, which is a characteristic feature of long-range order, followed by a straight line, and then deviates downwards at high temperatures, this last trend being characteristic of a disordered state. So in the middle regime, the slope is equal to unity, which enables us to then say that nu is infinite, which is concordant with what one would expect within a BKT phase. So reporting this range onto the graph with temperature, we are able to have an estimate of the location of the BKT phase, and you see that it's rather narrow, since it occupies only 5 Kelvin spread above TC. So another characteristic features of BKT phase and phase transition is the fact that the two-point correlation function changes behavior upon crossing TBKT. So we have computed the correlation function, and we show here, for instance, for the paraelectric phase, we see that the data is well fit with an exponential decay, which is characteristic of a short-range order or a disordered phase. Within the BKT phase, however, the data is better fit with a power law, which seem to once more be in line with the BKT scenario. So extracting this eta exponent from the power law fit and the critical and the xi, the correlation length, from the exponential fit, we can track the evolution with temperature of eta and the correlation length. And we find that eta, which should have a value of 1/4 as at TBKT, does indeed acquire this value at a temperature that coincides with our previous location of TBKT using the Binder cumulant. So yeah, it happens around here, which is the upper bound of the TBKT, of the BKT phase. The correlation length that we have extracted features an exponential divergence above, upon reaching TBKT from above. So this is its essential singularity, and linked to a new exponent that is infinite that we just showed previously in the previous slide. So now, so we are basically having in hand some signatures of the existence of an intermediate BKT phase. However, as stated at the very beginning, such a phase is characteristic of a continuous symmetry, and thus we should expect some kind of delicate balance between the discreteness or the anisotropy and the isotropy of our Hamiltonian, so as to allow the emergence of some kind of continuous symmetry that would support the BKT phase that we've seen. So we have, for that, computed the symmetrized probability distribution of the local dipole moments, which is basically the internal state space, and we've checked the evolution of its topology with decreasing temperature. So as you can see, we are in presence of 3 distinct phases with 3 distinct topologies. At high temperature, we have a uniform distribution around 0, and upon lowering temperature, the dipoles acquire a non-zero magnitude, which makes the distribution ring-shaped. And upon decreasing temperature further, we recover the 4-fold degeneracy of the ground state, which is what's left of the cubic symmetry when restricted to 2 dimensions. So we do have indeed, it seems like it at least, that in this intermediate temperature range, so within the BKT range, we have an emergent continuous symmetry where the anisotropy only slightly distorts, as you can see, the shape of the ring, but basically guarantees, given the theory of Merman for topological defects based on homotopy theory, that any topological defect, point-like vortices or anti-vortices, would be stable in this intermediate phase. So, comforted with those observations, we went on probing vortices and anti-vortices, since this transition is, after all, of a topological nature. So, at very low temperature, we do find that the anisotropy fully reasserts itself, in the sense that it is responsible of a truly long-ranged order phase and fully devoid of topological defects. In this middle BKT phase, we find that topological defects, vortices in blue, anti-vortices in red, occur in tight bound pairs, so they concentrate the distortion and they allow the correlation of the dipolar field to have a certain extent, I mean the power law decay basically. When we increase temperature further, they proliferate and also start to display an unbinding dissociative behavior. And this dissociative behavior, together with this proliferation of defects, is responsible of the breaking down of any kind of, significant correlation in the vector field. We looked closer into this unbinding process that is characteristic of the BKT transition, and for that we looked into the minimal distance and its evolution with temperature, so minimal distance between vortices and anti-vortices. And we find that this quantity experiences its most abrupt increase at TBKT, which seems to confirm the BKT picture of viewed through the topological defects. So actually for the BKT phase, it's the dynamics of topological defects that are the most important. So to assess whether we are in presence of such dynamics, although this part is still at its preliminary stage, we have done some molecular dynamics, and we have computed, for instance, the real-time autocorrelation function of spatial distribution of defects within the BKT phase here is shown. And we see that this autocorrelation with time features a decay, which signals that the topological defects are mobile entities. They diffuse. So here I present two snapshots that are consecutive in time, below TBKT and above TBKT. So below TBKT, we see that the pairs diffuse as a whole. So, so the defects do not diffuse freely or independently. They are confined within these pairs, and it is this diffusion as a whole that warrants the quasi-long-range order. Above TBKT, we see that defects diffuse independently, and this is again responsible of the breaking down of the correlations. So we are here facing a very delicate balance, given the dimensionality within which we constrained our system to be, between anisotropic and isotropic contributions to the Hamiltonian. So the effective Hamiltonian that we've used combines isotropic and anisotropic terms, and they're often mixed within the different energy composing it. For instance, if we look at the on-site or self-energy of the local dipole moments, there is this expansion parameter gamma obtained from first principle calculations, but that we see monitors the strength of the anisotropy. So if to test our intuition about what's happening, we set it artificially to 0, just to see whether if we decrease the anisotropy, we would enhance the BKT, since it seems that the balance goes in this direction. So we set it to 0, and we did indeed obtain, we reiterate all the Binder analysis, and we did obtain an extended range with respect to the one mimicking the real model, the real system. So here it was about 5 Kelvin, and decreasing the anisotropy made it extend on about 13 Kelvin. So we think that that these results should hold for any type of ferroelectric, provided that the balance is delicate enough between these two contributions. Also, our results seem to be consistent with a model that perturbates the 2D XY model by adding a fourfold anisotropy field, symmetry breaking field, so that can be viewed as reminiscent of what's left of our cubic symmetry in 2D. And in this model, they show that depending on the strength of the anisotropy, so let's say if we take the asymptotic limit where the anisotropy is at its strongest value, then we will suppress the BKT phase fully. And in the other limit, if the anisotropy is decreased to 0, then we would suppress the ferroelectric phase fully, since we will be in one-to-one with a 2D XY model. So in summary, using scaling, symmetry, and topological kind of arguments, we have gathered what seem to be evidence for the occurrence of an emergent continuous symmetry at criticality. So it is emergent in the sense that it's not an exact symmetry of the Hamiltonian, which is discrete, and evidence also for the fact that this quasi-continuous symmetry supports a BKT type of behavior. Other studies that you have performed, but that I cannot expose today, further exemplify the non-negligible role of topological defects in ferroelectrics. For instance, we found that they correlate to the relaxer behavior in BZT, PSN, that we have tested, for instance. The paper is submitted for now. And we have also found that in a BST nanocomposite that goes through a chiral symmetry breaking, that different chiralities provoke some kind of orientational boundary condition that cannot be fulfilled, and that provokes geometric frustration. And we found that the topological defects actually remain floating up to the lowest, down to the lowest temperature, which puts them in connection with the residual entropy. Also, we have characterized the topological nature of a skilmunic state within ferroelectric nanocomposites. Thank you for your attention.
Okay, thank you. Questions? Henry, I'll bring you the...
So can you, in those real space pictures, I didn't get a sense of what you meant by the quasi-long range order
yeah.
In those snapshots. Could you just give me a better feeling for that?
Yes, so the picture is rather small, but you see, if you look here, for instance, in this region, you see that the dipoles are rather correlated, but on length scales that are not that of full order. I mean, the correlation is not constant throughout space. But there are small regions where the dipole configuration feature an extended correlation. So it's a power law. It means that the correlation drops less fast than in the exponential behavior characteristic of a disordered system. So we are in between a state of real order and no order.
Any other questions?
Just to clarify, so when gamma equals 0, in your simulation, do you see ferroelectric phase or not? Because
yes, you mean here in this?
Yeah.
Here. Yeah, TC is shifted down.
But in the, then you have the continuous symmetry. Then
yeah, but it's in reality there are many anisotropic. The way the effective Hamiltonian is built and designed, it contains several contributions to the energy, and here it's just one part of the energy.
So you are not using that effective Hamiltonian. You are using something different, because that one, if you get rid of gamma, you don't.
Yeah, no, it's just that I kept all the same. I just took one energy term, which is the self-energy of the dipole moments, and I looked at the anisotropic contribution in this term only, and I switched it off.
I see.
So I didn't erase the anisotropy. I just artificially made it a little bit less screaming. So this resulted in a drop of TC, meaning that the ferroelectricity became less robust, and also resulted in an extension of the BKT phase.
Okay. Any other questions? Okay, let's and now the moment you've all been waiting for. I'll turn it over to Peter. And I should say, Peter Gehring did all of the work for the organization of this meeting.
Not true.
And deserves a big hand of applause. I'll turn it over.
Yeah, I definitely want to thank Michelle Schultes, who's Carnegie too. I definitely want to thank Carnegie. They've provided a lot of funding. I don't know if these people are still here. But the winners were awarded accordingly, and I want to say that everybody did a fantastic job, but there were some clear standouts. In other words, these people were listed on all the ballots, and that's something that I was worried about, is it would have a close call, but there were very much standouts. Everybody did a great job, but I'd like to congratulate Stella Skiadopoulou, and I apologize if I haven't pronounced that right, Elena Glazkova, and Diomedes Saldana Greco. So we should all let them stand if they're here and give them a round of applause. Okay. The reason why there are 2 theory prizes, remember I announced that there'd be 2, is actually when we looked at the categorization, there were far fewer experimental posters than there were theory. We thought it unfair, so we're going to split the 2K hopefully equally among all the prize winners. So I want to close the session now. I want to thank Carnegie very much for their financial support. Ron and Zoe did a fantastic job. Michelle Schultes down at the registration desk was absolutely essential to our operation. And we hope to see you next year. So, safe travels.
I guess we're going to the Whole Food or this Queen or whatever, because we have the tax. Oh, right. Actually, today we went to the restaurant. We arrived half an hour late.